Hello, chemists. We're back again to talk about spectroscopy, and this time, instead of focusing on the instrumentation, we're going to talk about one of the methods that most people use to talk about spectroscopy or to use spectroscopy in the lab, and that is Beer's Law. Now, you may have done a little bit with Beer's Law in Gen Chem 2, maybe, but we're going to dive a little bit deeper into it here. So, it's really called the Beer-Lambert Law. I'm not sure who Lambert was, but he gets forgotten a lot in this particular instance. So, the Beer-Lambert Law is essentially a relationship that says that the correlation between the level of intensity, absorbance, is linear with respect to concentration to a certain extent. So there are some limitations here. But this goes with the fact that concentration and absorbance have a linear relationship. And so when we plot that, here on this axis we have concentration, on the y-axis we have absorbance, and we get some relatively linear data points, and then as we go to higher and higher concentrations, those tend to level off. I'm going to see how straight a line I can draw here. And my straight line. And you can see, let me choose a different color here. You can see that we sort of, the actual data tends to drop down. And so the level at which this drop down occurs depends a lot on the material, the compound that we are investigating, which compound we're talking about in terms of concentration. The main reason for this drop off is that if we have our cuvette here, if it's got just a few particles in it, then as our light waves come in, there's plenty of photons around that every molecule can have its own photon and can absorb, and so we'll get some absorbance. But as we get more and more concentrated, we run into limitations where we're just not producing enough photons that every molecule can have its own. Or, sometimes more likely, it's so dense that a particular molecule in front, I'm going to switch colors again, a particular molecule in front is sort of blocking the molecules behind him. They're in his shadow, and so they can't absorb a photon because they're in the shadow of that front particle. So both of these lead to this loss of linearity as we get to very high concentrations. Okay. Beer's Law, again, I guess I'll continue to call it the Beer-Lambert Law. If I were Lambert, I'd want it to be called that. Relates absorbance to concentration through a couple of relationships. So we have absorbance here, we have concentration and molarity. Then we have these other two terms. B is the path length, sometimes called the cell length, And that's the actual distance of the cuvette, the width of the cuvette that the light passes through. And so this distance here is B. And then this last one, epsilon, this is our molar extinction coefficient. This is sometimes called molar absorptivity. And it's essentially that relationship, that factor by which we scale, by which we relate the concentration to the absorbance, that molar absorptivity, molar extinction coefficient. A couple of things to point out here, right? This is, of course, a linear relationship, so as the concentration goes up, we expect the absorbance to go up. As the path length goes up, we expect the absorbance to go up. And as our molar extinction coefficient goes up, we expect the absorbance to go up, right? This is just a direct relationship. Because this is linear, I'm going to rewrite our equation. We can think about this as y equals mx plus b. Well, there's no plus anything in our equation here, but in parentheses, I'm going to put plus 0. What this lets us know, right, is that at a concentration of 0, the absorbance better be 0, right? Remember, B is our y-intercept, and so where the concentration goes down to 0, the absorbance should also go down to 0. It's not perfectly true all the time, but generally speaking, it should be pretty close to true. And so we can think about this as m times x. We know that absorbance is our y. We know that molarity is our x. And so epsilon times b is our slope. And so again, I'm just going to sketch in this little graph here. We have concentration versus absorbance. And so the slope here, m, equals epsilon times b. In many, many cases, b is 1 centimeter. And so epsilon and slope are essentially the same. Let's talk for a minute about units. And so A equals epsilon Bm. The absorbance is unitless. This is molarity. So this is moles per liter. This is often given in centimeters. It doesn't have to be, but by far the most common unit is centimeters. It has to be some kind of meter. And so in order to end up unitless, epsilon has units of liters per mole times 1 over centimeter, so liter per mole centimeter. Right? Be very careful about units and just make sure you're including the right ones. Okay. Real quick, a little problem. Right? If we have some data points, and let's say that we plot our trend line and we get a slope of 1427. Right? Remember, that's epsilon times beta. 1427, as long as we're in a 1 centimeter cell, then B is 1. So then epsilon is 1,427 liters per mole centimeter. If we run, so these 5 were standards. If we run an unknown, and that unknown shows up right here, at an absorbance of 0.76, 1, I'll give this 3 sig figs. 0.761, what's the concentration of that guy? Well, 0.761 equals 1,427 liters per mole centimeter times 1 centimeter times our concentration. I don't need to know the concentration of each data point as long as I know epsilon. Right? On the opposite end of things, if I don't know epsilon, then I need to know the concentration of each data point so that I can find the slope and make an epsilon calculation. And so, we're going to throw this in the calculator. And we get a concentration of 5.33 times 10 to the negative 4 molar. Generally speaking, with Beer's law, we need to keep things relatively dilute in order to have a good linear curve. This example had an epsilon value of 1400. That's probably about an average value. Some things are small, like 300. Some are real big, like 8,000 or 10,000 even. But I would say most colored compounds sort of live in the range of a few thousand liters per mole centimeter. And so our concentrations really do need to be relatively dilute in order to use Beer's law. One more thing. When we look at our curve here, not our Beer's law curve, but our absorbance versus wavelength. I'm going to do this in nanometers. Again, we were about 400 to, let's say, 700. We have our nice broad absorbance curve. Usually, we choose our highest wavelength to measure our absorbance. This is lambda max. If we choose, say, a point over here to measure our absorbance, maybe there's an interfering species or something like that. But if we choose a second point as our measurement wavelength, then we won't be able to use any epsilon values that we find in the literature. Almost always, epsilon values are taken at lambda max, and so this would be epsilon of, oh no, what is that? That's maybe 570 nanometers. And this over here is going to be an epsilon value of 500 even. Okay? Because these have different absorbances, they're going to have different epsilon values. Once we find epsilon, we have to make sure that we state what wavelength it's at, because epsilon varies with wavelength. What we could see, if we were to look at the Beer-Lambert law at different epsilons, something like this would be at lambda max, and I want you to figure out whether something like this would be at lambda measured, or something like this would be at lambda measured. Okay. Expect a question like that on our spectroscopy little quiz thing. All right, that's a little bit more about Beer's law and how we use Beer's law. That's from chapter 18 and a bit of 19. All right, take care.